thank you very much for that introduction. So this talk is specifically about how to estimate the long-term effects of a program, and I think there are two main takeaways I want you to get from it. Firstly, how economists, and in particular microeconomists, think about long-term effects and the methods we might use to estimate them. And then secondly, my research on how to estimate long-term effects and whether this method that we've generated works well. So, why do we care about long-term impacts? Well, I think long-term impacts are important in many different domains. Christian gave a talk earlier today on whether we could predict the impact of our actions now on the far future of humanity in thousands or millions of years. So clearly these super long-term impacts are important. However, I think our focus shouldn't solely be on these super long-term impacts, but on these short-term long-term impacts, essentially. So short long-term impacts, to be slightly awkward. There are a couple of reasons why we should focus on these. Firstly, I don't think we know yet whether we can predict long-term outcomes, even on the range of sort of 5, 10, 20 years. So it seems pretty clear to me that we want to make sure that we can do this for a 10-year period before we think about doing it for a 100-year period. Secondly, these short long-term impacts are also important in and of themselves. GiveWell recommends deworming mostly on the basis of one randomized controlled trial, which found that deworming during childhood had persistent impacts on outcomes like adult income, food consumption, and health 15 years later after the deworming. Now, this randomized controlled trial was run in part by a Giving What We Can member and one of last week's Nobel Prize winners, Michael Kremer. And it's a really excellent RCT. It's studying a really important topic, and it's doing it really well and producing lots of policy-relevant information. The problem with these long-term randomized controlled trials is that they're super difficult to do. You have to follow like thousands of people over dozens of years, and it's really difficult. You have to have a lot of patience, a lot of planning, and a lot of foresight. So the question is, given that we don't want to wait 20 years and don't want to go to all of this effort to estimate these long-term effects, how can we do it? How can we estimate long-term effects without having to wait a long time? So this problem is a problem that's faced in medicine quite a lot as well. Medics often want to know what the impact of some new treatment or some new drug is on a long-term outcome, such as life expectancy. So how do medics approach this? They break it down into 3 steps. So let's say we're trying to estimate the impact of some new surgery to cut out a tumor, a cancerous tumor, on a long-term outcome like life expectancy. So the first step medics would do would be to look at the effect of the treatment on some short-term outcome, or some surrogate outcome to be more technical. So in our case, we'd look at the effect of the surgery on tumor size. Then the second step would be to look at the relationship between our short-term outcome and our long-term outcome. So we look at the relationship between tumor size and mortality rates. Now, once we have these 2 pieces of information, we can combine them. We can then combine the information on the effect of the surgery on tumor size and the relationship between tumor size and mortality rates to back out the effect of the surgery on life expectancy. So this method works well in medicine because there's often only one mechanism, one channel through which the short-term treatment affects the long-term outcome. That is, the treatment only affects the long-term outcome of life expectancy through tumor size. In social science, this assumption is much less credible. There are many different mechanisms through which any given treatment can affect long-term outcomes. So how can we deal with this? A recent econometric theory paper by some other economists who will probably win the Nobel Prize in the future, if you're a betting person, has generalized this method to work with many different outcomes, many different short-term outcomes. So how does this method work? We need 2 data sets for this method. The first one is an experiment, and the second one is an observational data set. So in this experiment, we have our randomly assigned treatment, this T. We have, so let's say this is cash transfers, for example. We then also have baseline characteristics. So these are characteristics of the recipients of the transfer that are fixed at the time treatment is randomized. So these could be things like the education of their parent or their age. Then finally, we have the short-term outcomes in the experiment. So this would be outcomes like whether you were enrolled in school, what your test scores are. In the observational data set, we don't have a randomized treatment. That's why it's observational. So for this, think of things like censuses or household surveys. We need to have the same baseline characteristics and the same short-term outcomes that we have in the experimental data, but additionally, we need information on the long-term outcome that we care about. So let's say this is whether you've enrolled in tertiary education, whether you go to university. If we had this long-term outcome in the experimental data, there would be no problem, right? We could just take the average of the long-term outcome in the treatment group, subtract the average long-term outcome in the control group, and this would give us the impact of the treatment because of the random assignment. So we can think of this almost as a missing data problem. We don't have a Y, a long-term outcome in the experiment. So how can we get it? So there are 3 steps to this method. The first step is to take the observational data and estimate a predictive model from it. So with this model, we predict the long-term outcome as a function of the short-term outcomes and the baseline characteristics. So our model tells us what the relationship between the long-term and the short-term is. We can use a simple method like linear regression for this, or we can use super fancy machine learning methods, whatever you fancy. The second step then is to take this predictive model from the observational data, this H hat 0, and we can use it then to predict Y in the experiment. So we fit this model to our data, and we feed in the information on the short-term outcomes and the baseline characteristics in the experiment, and this produces predictions of the long-term outcome in the experiment. Then once we have these predictions of the long-term outcome, we can treat them as if they're just the actual long-term outcome. We can take the average long-term outcome, predicted long-term outcome in the treatment group, the average predicted long-term outcome in the control group, and the difference between these is the predicted impact of the program, even though we don't have actual information on the long-term outcome. So this is the surrogate index method. The original paper also introduces another method, the surrogate score method. That's slightly less intuitive. I don't have time to go through it, but all you need to know is it requires on exactly the same data as this and exactly the same assumptions. So what are the assumptions we need for this to work? The first assumption is the main one, which is surrogacy. So what this says is treatment is independent of the long-term outcome, conditional on the short-term outcomes and the baseline characteristics. So this is slightly confusing and almost meaningless, but luckily we can represent it in a graph, which is hopefully more clear. So we're saying that the treatment has an impact on the short-term outcomes, this S. The short-term outcomes have an impact on the long-term outcome, and the baseline characteristics have an impact on both the short-term outcome and the long-term outcome. But there's no relationship between the treatment and the baseline characteristics because the treatment is randomized. What the surrogacy assumption requires is 2 things. Firstly, that the treatment has no direct impact on the long-term outcome. That is, there's no arrow going from T to Y there, from treatment to long-term outcome. What this means is that the entire effect of the treatment on the long-term outcome must flow through the short-term outcome. These short-term outcomes must mediate the full impact of the treatment on the long-term outcome. The second assumption is that there are no unobserved baseline characteristics that affect both the short-term outcome and the long-term outcome. There's no of these U variables. Any of these characteristics which affect both outcomes must be observed. They must be in this X. So this is a pretty demanding assumption. We're saying we need all of these channels through which the treatment affects the long-term outcome, and we need all of these potential confounders between the short-term outcome and the long-term outcome. So it's demanding, but also it becomes more credible the more data we have. The more short-term outcomes we have, the more of these mechanisms between treatment and the long-term outcome we can account for, and the more baseline characteristics we have, the less likely there is to be an unobserved one that affects both the short-term and the long-term outcome. So this is the first assumption, the surrogacy assumption. The second assumption now is the comparability of samples assumption. What this just says is that the long-term outcome, or the distribution of the long-term outcome conditional on the short-term outcome and the baseline characteristics is the same in both the experimental and the observational data. So why do we need this? Well, remember that we use our observational data to estimate a predictive model. We're estimating the relationship between the long-term outcome and the short-term outcomes. If the relationship between the long-term outcomes and short-term outcomes is different in the experiment and the observational data, then obviously this model won't produce good predictions of the long-term outcome in the experimental data. So this is why we need this. So if these 2 assumptions are satisfied, and a couple of other minor technical ones, then the surrogacy approach should work. We should be able to predict long-term estimates of treatment. So the question is then, do these assumptions hold in real-world data? So I take long-term randomized controlled trials from development economics, where I can exploit the fact that I have information on the treatment, the short-term outcomes, and the long-term outcome, so I can compare the true long-term outcome from the RCT with an implementation of my surrogacy method. So the data I use is from a recent paper by Barrero-Sorio and co-authors, and they're studying conditional cash transfers in Colombia. So they have 2 randomized controlled trials. One takes place in San Cristobal, and here they have 2 treatments. The basic treatment, students are randomly assigned to either the basic or the savings, and those in the basic get given $30 every 2 months, conditional on being enrolled in school. The savings treatment students only get $20 every 2 months, but they additionally get $50 at the start of every academic year as a way to encourage them to buy school uniforms and school supplies and ensure they return to school. In SUBA, in this second randomized control trial, the treatment is also $20 every 2 months, But instead of $50 at the start of every academic year, it's $300 conditional on enrolling in tertiary education, so to provide a strong monetary incentive for students to continue their education. So the original paper studies the effects on both short-term outcomes and long-term outcomes. So the short-term outcomes they study include things like enrollment, things like whether students have graduated from secondary school, and whether they've enrolled in tertiary education in 2012, so 8 years after the start of the program. The long-term outcomes are observed 12 years after the start of the program in 2016, and these are information on whether students have enrolled in tertiary education again, whether they enrolled on time, and whether they've graduated from tertiary education. The headline results of this original paper are that the basic and the savings program have 0 long-term effect, while the incentive program has a positive long-term effect. So this is the data I use, but how do I use it to test my surrogacy method? So let's take SUBA as our experimental data. Because we have our treatment, our baseline characteristics, our short-term outcome, and our long-term outcome, we can estimate the impact of the treatment on the long-term outcome. We just take the average of the long-term outcome in the treatment group and the average of the long-term outcome in the control group, and this gives us an unbiased estimate of the effect of the treatment, the long-term effect of the treatment. We can think of this as the true effect that we're wondering if the surrogacy method can replicate. So now let's implement the surrogacy method. Let's pretend that we don't have long-term data. We don't have this Y in the experiment. So we just have treatment, baseline characteristics, and short-term outcomes. This now mimics the experimental data set, the short-run experiment that we need for the surrogacy method. Now we can go to San Cristobal and pretend that we don't have information on treatment status. We just have baseline characteristics, short-term outcomes, and the long-term outcome. This now mimics the observational data that we need for the surrogacy approach. So we've created these 2 sort of fake data sets, which we can use to implement the surrogacy approach. We take our data from San Cristobal, our observational data, and we estimate a model to predict the long-term outcome as a function of the short-term outcomes and the baseline characteristics. Once we have this model, we fit it to our experimental data to produce predictions of our long-term outcome. And then with these predictions, we compare the average predicted long-term outcome in the treatment group with the average predicted long-term outcome in the control group. So this produces a separate surrogacy method, surrogacy estimate. So are these results similar to the RCT results? So along the top here, I have my 3 different treatments. So for the incentive treatment on the far right, I'm taking SUBA as the experimental data and San Cristobal as the observational data. I can, of course, do the reverse and take San Cristobal as my experimental data, so that's for the basic and the savings graphs, and then SUBA is my experimental data. Along the bottom, I have my 3 different outcomes: enrolled, on time, and graduated. So the red dots are the true estimates from the RCT, the ones we're trying to replicate, and the bar around it is the 95% confidence interval. The green dots are from the surrogate index method that we explained earlier, and the blue dots are from the surrogate score method that we had to skip over. So what do we see? Well, I think the most notable thing is that the blue and the green dots are always within the 95% confidence interval of the RCT. This means they're never statistically significantly different from the RCT estimate. So this is good news for us. Even better than that, these dots are not only in the confidence interval, but they're often close to the center of it. So the actual estimates we're getting from these surrogacy methods are very similar to the actual estimates from the RCT. So I was pretty happy when I got this news. This method seems to work really well, and it's got potentially lots of use cases, and we can use it to predict long-term impacts. However, it's always good to test the robustness of your methods. How well do they work when we're not implementing them in ideal circumstances? So that's what I do next. So here, I'm re-implementing the surrogacy method, but I'm only using a subset of the short-term outcomes to predict the long-term outcome. I'm not using the full set of them. So along the top, I have my 3 different outcomes again: enrolled, on time, and graduated. And along the bottom now, I have different subsets of the short-term outcomes of the surrogates. So we start off the leftmost column in each graph with just information on enrollment in secondary school from 2006 to 2008. Here, the surrogacy methods are producing estimates pretty much exactly close to 0, which is also very far away from the RCT estimates. What this suggests is that these enrollment variables are not good surrogates. They're not mediating the impact of the treatment on the long-term outcome, and they're not predictive of our long-term outcome. So they're not helping us estimate our long-term effect. Next, I keep the enrollment variables, but I also add information on whether students have repeated grades, whether they've been held back, or whether they've dropped out of secondary school. The performance is almost identical again, and this method is not helping us to predict the long-term impact. Next, I add information on whether students have graduated from secondary school. Here, if we squint really hard, I think we can see a slight improvement in the methods, but we're still very far away from the actual RCT estimate. And finally, I forget about all these other variables, and I just take information on whether students have enrolled in tertiary education in 2012. Now, the method seems to be doing much better, right? The point estimates, the dots, are much closer to the RCT estimate. So what does this mean? This means that these variables on whether you've enrolled in tertiary education by 2012 are the ones doing all the work. These are the variables that are mediating the long-term impacts. They're predictive of the long-term outcome. So to some degree, this is really unsurprising. Of course, like tertiary enrollment in 2012 is going to be predictive of things like tertiary enrollment in 2016 or tertiary graduation. So what I think this highlights is that the surrogacy method can work, but it's very sensitive to having these key surrogates, these things that are predictive of the long-term outcome. So to summarize, I've tested a new method to estimate long-term effects, and sort of the headline conclusion is it works well on this 4 to 5 year time frame. But once we go longer, sort of 10 years or so, and we have less of these short-term outcomes, we're really struggling with this method. It doesn't work so well. So I think the broader takeaway here is that estimating long-term impacts is really, really hard. It's very difficult to do. Here, we have an RCT, and we're only trying to predict impacts over 10 years, and we're still really struggling. So I think this means we should be pretty skeptical of strong claims that we can predict the impact of our actions now in 50, 100 years, or even greater. However, this is just an economics perspective. I think it's highly likely that other disciplines have much better methods for estimating long-term effects, so I'm very interested in learning about those. I'm doing work on testing this method in different contexts, because currently I just know how it performs in one context, and maybe it performs better in other ones. I'm also doing work on trying to improve the method to work in longer time frames and use fancier machine learning things. But this is just the econ perspective, like I said. I'm very interested in hearing more from people who want to estimate long-term impacts. So people in climate science, people in forecasting literatures often have insights which I think would be very useful. So if you're interested in this topic, please ask a question in the discussion. Come grab me afterwards or send me an email. Thank you very much.
Thanks very much, Sophia, and thank you very much, David. So, yeah, can we switch over to slides? Cool, great. So I'm going to give a kind of summary of what I think Dave's contributions are. And I think this is a big and important question. So as David said at the beginning, there's a kind of deficit of evidence on long-term effects. I think this paper kind of helps address key challenges related to 2 EA causes. So the first is global poverty, where the application is quite clear, but possibly other kind of short-termist causes like animal welfare, where there's just this lack of evidence on longer-term effects of interventions. And here I'm talking about 5 or more years. And in these cases, whether these effects that we see in the short term in an RCT are persistent might dominate the kind of accuracy of the short-run effect. So to kind of give you some examples, if you kind of dig into GiveWell's cost-effectiveness analysis, quite often one of the really important factors is how long they think these effects are going to last. Like, are they going to last 5 years or 20 years? That can play a big role in the strength of evidence behind an intervention. And then these are some academic papers. So Blattman et al. Looks at a kind of cash transfer program in Uganda and finds that after 9 years, the kind of treatment group converges with the control group. And then these 2 other papers by Banerjee et al. And Bandiera et al., they actually find good evidence of long-run persistent effects of targeting the ultra-poor programs. So these are programs which kind of combine cash transfers or a productive asset with some training and some other interventions. So here, like basically the evidence on persistence of effects is normally quite small. We have a few examples where it turns out to be really important, but generally it's quite hard to do, as David kind of concluded with. And this seems like a potentially useful method to improve the accuracy of our estimates over the long run. The second area is to do with long-termism, where it's essentially very hard to predict very long-run effects over further timescales, so 20, 50, 100, maybe 1,000 or more years. And I think Dave makes a pretty good case that we need to make some progress on this. And within the field of economics, we're pretty terrible at this. And so I pulled this quote out from David's paper where he says, "It's probable that if we're not able to first predict the impact of our actions in 10 years' time, we'll also be unable to predict their effect in 100 years' time." And I think that's pretty compelling. And then David also has this kind of term, marginal long-termism, where he kind of argues that one way of kind of doing better on long-termism is to push people on the margin to think about longer-term effects. And so I think this work can help contribute to that. And what David does in this paper is he basically takes a recently developed technique by these future Nobel Prize winners, Athi, Imbens, Raj Chetty, and Kang. Yeah, look out for them if you do want to place your bets, as David suggested. It's pretty good bet, I reckon. So yeah, they've developed this technique, but as far as I know, this is the first empirical application and test of this multiple surrogates approach. Yeah, they basically put this paper out there in 2016. There hasn't been much application, so I think it's great that David's kind of taken this and applied it to some real-world data. So this might improve our estimates of long-term effects of interventions which have short-run evaluations, and David's results are encouraging. And it might help us make this incremental progress towards understanding very long-run effects. So just in terms of next steps, so I think me and David have discussed this before. I think next thing I think he might want to do is kind of understand the variance of these estimates better. So at the moment, he showed you point estimates of this application and where they land relative to the long-run RCT. He's got another application in a paper where he kind of runs some bootstrap simulations, which tells us something about the variance of the performance of the estimator. And then I think a key thing will be to look at additional applications, and especially those with larger true effects. So in the paper that David looked at, 2 of the 3 interventions kind of have a close to 0 or a not statistically significant effect. And my worry is that's not a very high bar to clear, because if there's a close to 0 effect on the intermediate outcomes and a close to 0 effect on the long-run outcomes, then you're obviously going to estimate a 0 effect on the long-run outcomes when you see the intermediate one. So I think David's got some ideas of like new papers to apply this to, so maybe we'll talk about that a little bit. And then understanding the relative performance of the 2 surrogate techniques. So David mentioned there's 2 different ways, and it's not clear from a theoretical perspective which one would perform better. And I think that's something to kind of explore. So I'm going to just pose a couple of questions and then let you respond, David. So yeah, the first one is there a theoretical reason to expect the bias to be towards 0? And if that is the case, then this might be a very useful lower bound estimate for the long-run effects in cases where we don't know the true effects. The second kind of question or comment is, do we have an understanding of when we might expect this method to perform well? So you started to do this in your last few slides, where you showed that different combinations of the intermediate outcomes perform in a variety of ways. And if we don't know the true effect, would you kind of be confident of saying, well, this data set seems to have the correct surrogates? And my sense is this is quite hard to know, and it will be not a science and more of an art of trying to understand when this method might perform well. I have some suggestions that maybe we can discuss afterwards of, can you develop a kind of informal test of this if you have multiple rounds of surrogates, and then you want to project that into the future? And similarly, can you kind of develop decision rules as to which are 2 estimators to use, and how to implement the estimators? So, for example, which variables do we need to include as a surrogate, or which variables do we need to include as a control? So I guess, yeah, I'd be interested to hear your thoughts on the bias towards 0, whether you have a sense of when we expect this to perform well, and if you have a good sense of how we might implement this. And then remember to submit audience questions on a Hoover app, because then we'll switch to them. Cool, over to you, Dave.
Okay, so yeah, start at the beginning then. So theoretical reasons to expect a bias towards 0. So I think your point is exactly right, that if there's no intermediate effect, then obviously we're going to predict no long-term effects, and yeah, this is just almost mechanical, essentially. However, if we are in cases when there is an intermediate effect, I don't think there's any plausible reason why we should expect there to be a long-term effect estimate of 0.
Yeah.
This is for the surrogate index method. For the surrogate score method, instead of doing predictions of the long-term outcome with the observational data, essentially you do predictions of whether someone is treated in the experimental data. And sort of just the structure of this estimator means that if your predictions here are biased towards 0.5, random, then that estimator is pushed towards 0. So that's a potential concern, but I don't think there's any reason to expect your predictions of treatment probability to be biased towards 0.5.
Okay.
I think, yeah, these predictions shouldn't be, like, if there is noise in them, it should be going both ways, up and down, not necessarily like, towards 0.5.
So we can't use that to bound our estimates in any predictable way?
I don't think so, no. But
Okay,
yeah,
okay.
I need to do more theoretical work on this as well, yeah.
Yep.
So next was, when might we expect the method to perform well? So I think the obvious thing is that the method works well when you use it over shorter time frames. Like in that case, the prediction problem is harder. You have more data to do the prediction with. So yeah, it's like clearly just going to work better then essentially. I also think like simpler interventions, it might work better. So cash transfers where like effects seem to be sort of persistent and slowly fade out. Like as long as there's some sort of like consistent pattern, I expect it to work better. The counterexamples of this would be deworming, where so in deworming we have sort of pretty large short-term effects, no medium-term effects, and then large long-term effects again. It's this really like confusing pattern that we don't really understand, and I think this method would not perform particularly well there. But yeah, as I said, it would also work better, like these more short-term outcomes we have, the more baseline characteristics we have. So that sort of leads on to the next thing then. So I would like to do a further test with the deworming data. But I'm waiting for it to come online, essentially. I've been promised many times that it will be online soon, and we're not quite there yet. But yeah, if you can nag someone, that would be very helpful.
I don't know if I have that power. So I'd be interested to hear a bit more about your other applications that you have in mind, and what papers are already available that you could apply this to. And then equally, what would be the kind of perfect hypothetical application where you could test this method? Like, what would that experiment look like?
So the other things I have in mind are deworming, essentially, and there are a few other sort of conditional cash transfer papers. The main problem is that these RCTs only started to be run sort of 20 years ago in development economics, so these long-run follow-ups are happening right about now. So people are trying to publish these like long-term results themselves, so they're currently not willing to share the data because they want to get their publications out. However, there are like a few cash transfer things, the Blackman paper you mentioned, where there's potential there. So I'm looking into those as we speak. I think from a sort of theoretical perspective, it might be nice just to stick with cash transfers to sort of make the analysis simpler and make the sort of conclusions at least strong for cash transfers, even if they're not strong for other things. But yeah, I would like to explore this across many different data sets, essentially. And your second question was?
About the hypothetical best experiment that you would test this method with.
So ideally, there would be like many waves of like short-term data, essentially. Like if you have sort of data collection 2 years, 4 years, 6 years, 8 years, 10 years after treatment, then that would like allow me to explore the effect. Like, can I use the 2-year outcomes to predict the 4-year outcomes, the 6 years, and you can just do all of these things. So the deworming data looks a little bit like that. I think they're on like 4 or 5 rounds of data collection now. So yeah, just again, waiting for that.
So yeah, if anyone in the audience has an RCT with 4 or 5 rounds of data collection, please get in touch with David. I think we're out of time. But yeah, thank you very much everyone for coming.